Hello everyone and welcome back to another video. Today we'll be taking a look at a continued look at a chess engine in Python. So in this particular video, we'll be taking a look at the best move function. So what this does is this basically determines what the best move in a certain situation is. So this basically draws in all the other functions which we've been doing in the past couple of videos. So namely, for example, the evaluation functions as well as the legal move functions. So it basically determines what all the possible moves are, and then it evaluates all of them, and then whichever one has the best evaluation for a particular color, that's evaluated to be the best move, so that's the one which is returned. So all of this is taken care of by this one function, best move. So now let's have a look at this in code. Okay, so if you're following along on GitHub, as I would recommend you do, it's basically on line 597 over here. It's nearly line 600. This is basically the best move function. So this is probably the most important function, like the most important single function in the entire engine, since this is the core of the function. It determines what exactly the best move is. Okay, so now let's just have a look at a brief overview of what exactly we need the function to do. So basically, an evaluation of a certain position basically depends on which color you're looking at it from, right? Since a certain position could be very good for black, but then very bad for white. So then in that particular situation, the evaluation would be negative. So this is how the evaluation is defined in chess. Like for example, -3 evaluation would correspond to about 3 pawns of advantage for black, or like about 1 knight or 1 bishop of advantage for black. So which is why we basically need some sort of evaluation. And then what this does is that this basically give it each of the possible moves inside all possible moves, which we looked at in a couple of videos ago. It basically plays all those moves out on a board, and then from each of those board positions, we basically make use of this evaluation function, which we've written a few videos ago, which determines the static evaluation of a board. And then it basically orders them, it sorts them by how good the evaluations are. Okay, so now let's have a look at the code. So first of all, if the color is 0, then we basically initialize this array to being float infinity for each of the positions. So what does this exactly mean? So we basically just initialize some null evaluation for each of the positions, and if the color is 0, then that basically means it's black, and if it's black to move, then the worst case scenario for black is if it's checkmate for black, which would be the case if the evaluation is float infinity, i.e. positive infinity. So which is why we initialize all of them to float infinity, and then that's just so we can basically identify which moves are valid or not. This is just like a base evaluation. We'll be changing all of these evaluations later. We'll be changing the value of these later depending on which board position it is. But then we're just initializing it to a certain default variable, if you like. And now what we do is we initialize this king array. This will come in handy a bit later. But then this bit of code just determines which positions are for the king. And then what we do is we basically iterate through all possible moves. And then for each of the possible moves, which could be made, what we basically do is we get the start square and the end square for each of these moves, and then we carry out that move on a particular board. Now, one important thing is this board needs to be a copy of whatever the original board is, and as well as the new piece locations need to be a copy of whatever the original piece locations are. And now both of these are going to get updated by the move function over here. And now, after we update the move function, then we basically perform an evaluation, a static evaluation of the position, if you like, based on grid copy, okay? And now after we get this certain evaluation, then we can use that later on. And now we have the static evaluation of the particular position. We basically increment counters, so this counter is just it's not really anything. It's not really part of the code. It was just meant for my own purposes to see how many positions we were evaluating in a given second. So which is why I had that counter, but that's not really relevant. So and now what we basically do is one important thing for this is that we need to determine whether the king has been captured or not. Since if in a certain position the king is not actually on the board, then it's not really a valid position, right? So if the start square in king, so that basically means that if the move which we're doing is a king move, then we need to basically update the new king's position. So if the king's if the king 0 is start square, so that basically means the first corner of 0 is start square, Then we basically make the second coordinate n square, and then the first coordinate n square. Okay, so this might have been a bit confusing, but like I'll go over it in a bit more detail after we go through the other ones, since trust me, this is not really that important compared to the other functions which we have. Okay, so and now this is pretty fundamental. So what we basically do is for each of the colors, we need to determine like where exactly that particular position falls. So let's say let's say if we're currently operating, if it's black to move, and then the positions which are already evaluated are -5, -4, -3, etc. Excuse me, and we have a certain position which is -4.5. So we basically need to slot that into the correct place within the sorted list of all the possible positions. So it won't quite be as good as a -5 position for black, but it won't be as bad as a -4 position. So we'd put -4.5 in between the -5 and -4. Okay, so which is why what we basically do is we iterate through all the number of moves, and then if the evaluation is less than maxi, then that basically means that we insert it in that particular position. And now that's if it's black to move. If it's white to move, then it's the exact opposite. If the evaluation is greater than that particular position in maxi, then we insert in that position. So now the reason why we do that is because black is basically evaluated negatively. So for example, negative evaluations favor black, then positive evaluations favor white, which is why we have this, okay? Okay, so now what we basically do is, if the flag is set to true, then we basically create a copy of whatever the king, whatever the king array is. So the reason why we do this is because the king array, this basically needs to be, it needs to remain the same for future subsequent iterations of this, which is why we create a copy of the king array over here, and then after that we reinstantiate the copy. If the flag is set to true, which it is over here, then we reinstantiate the copy back into king. This is just to prevent the king's location from getting changed at all, so which is why we do this. Okay, and now finally, what we basically do is if this particular position, if the length of maxi being the number of moves which we evaluate in this certain position, taken as parameter, number of moves, if this is basically exceeded, then we basically need to pop whatever the rightmost element is. Since the rightmost element will be the worst evaluation, so we could just get rid of that, since we have all the other positions just before it, which are superior. Okay, and now all we have to do is just repeat this this entire procedure for every single possible move. So then, which is why we go through all the start squares, and then for each of those start squares we go through all the end squares, and then etc. etc. And then after we're done with all this, we basically just return the maxi array. So this maxi array is basically just the array storing each of the positions as well as their corresponding evaluations. Okay, so and now maybe let's just have a look at this entire best move function in practice. Okay. Okay, so now let's look at a sample position. So let's say if we were to play e4 in a certain position, black basically responds with knight f6. So sorry, knight c6. And basically, what I've done is I basically just got the bot to output all of the best moves, which it thinks, as well as their corresponding evaluations. Okay, so and now here's where something is worth mentioning. Basically, this best move just takes the static evaluation of a certain board position. It doesn't look into the future. For looking into the future, we basically need decide move, which we're going to be going over in the next video. But then decide move looks through in the future moves, best move only takes a look at the current position. So which is why over here what I've done is I've basically set the depth of decide 0 to decide move to equal 0. This basically means that it's basically going to be the same as best move on its own. But bear in mind this is not actually how our code will work in the future. But we'll cover all this in the next video, so don't worry if you don't understand what I just said right now. But either way, basically, our bot thinks these certain moves are the best. So b8 to c6, so this basically means knight c6, it thinks is minus 0.22. And then knight f6, it also thinks is minus 0.22. And then pushing either of the pawns. So, okay, so it basically thinks that moving the knights here and here, they're both minus 0.22. Moving either of these pawns, they're both about equal. And then the other moves are like, I'm pretty sure the other moves are like just random moves like b8 to a6. So this is basically moving the knight the opposite way, so moving the knight here. I think this is the fifth and sixth best moves after the two central pawn moves and the two knight moves. Okay, so now these moves won't necessarily be the best. Like for example, let's say moving the knight here, that's not necessarily that good. Excuse me. But then the reason why it's not good is because the bot can't currently look into the future. After it plays this move, it doesn't anticipate what white will play. So for example, white could play this after knight c6 is played, knight f6 is played. White could play e5, and then knight f6 doesn't look too good. Then you'll have to play knight d5, knight g3, etc. But either way, that's a topic for the next video. But I just wanted to give you like a brief overview of how exactly this move function is actually going to be implemented, as in like how exactly it like looks at these moves. But now let's cover a relatively minor function. This is basically the is middle game function. So what this basically does is this determines whether it's the middle game or not. And now, as you can imagine, this would be very useful in the evaluation, since if the current board position is a middle game, then that basically means that like the evaluation should favor certain king positions. Since if it's a middle game, then the king should be like tucked away in the corner. However, if it's an end game, then the king should be a bit more active, which is where this is a middle game function is. This basically determines whether it's a middle game or not. And the way it does this is it basically totals the piece value and like sees whether there's a queen or not. Basically, if there's a queen, or if the total piece value is less than 15. Sorry, if the total piece value is greater than 15. If either of these conditions are met, then sorry, less than 15, like my mind is kind of melting. But basically, if either of these conditions are met, and this condition is also met, then it basically means that it's basically the middle game. Since, let's just go through this line by line. So if there's a queen present for both sides, then that means it's a middle game, right? Since there's enough like material on the board. But either that, or if the piece value is less than 15 for either player, then it's also a middle game, okay? Then in either of these conditions are met, then it's the middle game. Otherwise, it will be the end game. And now, how do we actually determine these values? So total piece value, we basically just get from adding all the individual piece values. And then is queen, we basically get from ORing the value whether if any of the board positions are and 7 equals 5. So this basically means if the piece number of any of the board positions is 5, then we set is queen to true. Because here's what we basically do. We OR equal this value. So let's say if it's already true, and then if this value is false, it already being true means that we've already encountered the queen a few moves ago. Then that basically means that this will continue to be true. However, if this is false, and then we OR this, then it will basically be true, okay? So that's basically it. And if both these conditions are met, i.e. it's a middle game, like each player has enough material, then it'll basically be a middle game, which is why we do the AND of both of them. And then after that, we basically just return this value, and that determines whether it's a middle game or not, okay? So that's pretty much it for the middle game and best move functions. I really hope you enjoyed watching this video. Hopefully you learned something new about how we implemented these functions. And if you did like this video, please be sure to leave a like and subscribe. It would be very much appreciated. And I hope to see you in another video next time. Thank you very much for watching. Bye.